So, good morning again. In the previous class, we were talking about various types of weldings, right? So there was one common type of welding which is usually used in structural applications, which is known as arc welding. Okay, and within the arc welding, we saw there were two options. One was the kind of welding wherein the electrode itself has the filler material as well as the the flux. Okay, and the other option is wherein the flux is deposited separately and the electrode is purely made of the filler material, and that passes that moves in a mechanized manner. Okay, where the welding is to be done. Okay. And both approaches are fundamentally very similar. The challenge with the second approach, the good thing about the second approach is that it is atomized, right? So if you want to do very long welds with a very high level of precision and very high quality, then the second option is preferable. The challenge with that is that it is not very easy to do that on an inclined surface. So if the surface is not perfectly horizontal, all that flux material that you are going to deposit will roll off, right? Slide off. So it will not stay there. So therefore, you need a horizontal surface, at least in that neighborhood, wherever you are doing the welding. So I was able to see a lot of pipes are done with that method, but what they do is, since pipe has a circular surface and it is not possible for the welding to go on around the pipe, what they do is the welding uh, electrode stays in one position and the pipe rotates, so that the welding is always happening on a horizontal surface. Okay, and that's where the deposition of this flux takes place. Okay, the flux, I discussed the purpose of flux, so I'm not going to repeat it. You can always, it's also mentioned here. It provides the shielding atmosphere. Okay. The other type of welding was gas welding, and the gas welding typically is done without a filler material, but sometimes you may use the filler material also. So gas welding is, of course, it's a gas torch which melts all the metals that are involved. The base metal, if you are using a filler material, even that gets molten, and then they fuse together and form a weld. Okay. The second option that I was talking about in the arc welding is known as submerged arc welding. It is not same as underwater welding. Okay. There are options to do underwater welding also. That's a very specialized field. You can find more. I don't know a lot about that. You can find more information on the internet. I'm sure there is some credible information available on the internet about the underwater welding. Many a times there are structures which may have some damage, some rusting or something like that, which are underwater structures, and then you may have to do some kind of a repair in that situation, and that's when this technique is used. But that is submerged arc welding does not mean it's underwater welding. Okay. Then we had seen a couple of videos. So this video was about what the welding process, arc welding process entails. Then there was another video which was about submerged arc welding in particular. So there you might remember seeing that what happens once this flux that is deposited, it keeps fusing, or it keeps oxidizing when you do as the welding process goes on, and then after a certain length has been welded, this thing kind of automatically starts to separate from the weld. Okay, as it cools down, it starts to bow a little bit and separate, and sometimes it is very fragile, of course, and then it does not need a lot of effort to be separated from the final weld. And then on top of the weld, you will always have some kind of a slag deposit. You might have heard of this word slag when you were taught about how the steel is produced, right? So whenever you produce steel is molten, some impurities come onto the surface, and that is what slag is. Okay, so the similar kind of a slag forms on the surface, and that has to be removed. So you can grind the welded surface, or you can even chip off that slag. It's also relatively brittle material, so you can remove it easily. All right, moving forward to how to apply these welds in structural applications. Okay, so there are two types of primary welds, two primary types of welds: groove weld and fillet weld. And then there are some variations of these which can be classified as separate types of welds. So a groove weld is basically, as the picture shows here. So let's say you have two plates that you are welding together, So if you create a groove between the two plates, okay, so if you bring the plates very close together with some gap in between, so that gap can be called groove. And if you weld that gap, that is what a groove welding is. Okay, so that is groove welding. A fillet welding is slightly different. In case of a fillet welding, you weld two perpendicular surfaces, okay, and they belong to different plates. So this is how a typical fillet welding looks like. So you have one plate here, you have another plate here, the two plates come together, and here you get a flat, here you get two surfaces which are perpendicular to each other, and you weld them together, you fuse them together. Likewise, you can fuse them together here, and both of these are fillet welds. Okay? So that is the other type of weld. Then there may be options or varieties of fillet weld which are known as slot or plug weld and tack welding. Okay, so the pictures here, they represent slot weld or plug weld. So these are just a variation of fillet welds. Actually, what happens, it should be quite clear from the picture. The slot weld and plug weld, they are basically the same, except that in case of a plug weld, you have a circular hole, and in case of a slot weld, you have a slot. Okay. Um, Maybe I can draw a little to elaborate further. So I have one plate and I have another plate. They are overlapping, and there is a hole in between. On the first plate, let's say there is a hole. Okay. Looking from the top, I can see this plate, the first plate, and the second plate is under it. Okay, and there is this hole. That is this hole. Fine. So now what in this type of welding, which is called plug welding or slot welding, if it is a hole, circular hole, it will be called plug welding. If it is a slot, that is a longer hole. A slot is typically a rectangle accompanied by two semicircles. Then this becomes a slot. Okay, and this is a circular hole. So what I may do is I may do a fillet welding, if I may draw it here. I may do a fillet welding in such a way that it fuses the two materials like so. Okay, and likewise here, all around. Correct? So this is what a slot or plug welding is. And then there is a tack welding. Tack welding is not really for structural purposes, but it is often used to start a welding. Because before you start any welding, you have to first hold the pieces together. And that is where tack welding comes into play, a picture. I would strongly recommend that you watch uh, you can watch some videos on YouTube about welding processes. So you can search welding two structural members, welding plate girders, welding, something like that, and see what the process entails. So basically, let's say I want to, this was a different type of welding. This was slot and plug welding. But let's say I want to weld these two plates using groove welding, or uh, uh, groove welding or fillet welding. Either one, hardly, it doesn't really matter. So let's say these are the two plates that we want to weld together. Now, and let's say I want to go for a fillet weld. So weld will be going all around this plate. The two plates have to overlap each other for the fillet weld to work. Okay. So the weld has to go all around. Let's say I'm doing all around fillet welding. So what I may do is I may first provide a tack weld here. Tack weld is a small weld. It can be fillet weld, it can be groove weld. A small weld here, a small weld here, and a small weld here. And then I may move forward with the entire welding, the entire length welding. Okay, it is not a good idea to start welding from one end all the way to other end and then go around and then go around without holding the two pieces together. Even though you are supposed to clamp them together also, but in addition to the clamping also, you should first do the tack welds. So the first 4 welds that you provide, or first sometimes you may just do 2 welds. So for example, if I have one plate here and I have another plate, and I want to do a groove weld in between. Okay, so I mean, of course, the gap looks very big, but assume that this gap between the plates is relatively smaller. So what I may do is I may do a slight one end tack weld, then the other end tack welded. This I'll do while the plates are being clamped in the position. Then once I have done the tack welding, then the plates are strictly held in place. Then I will go from one end and welding the whole thing. So these will be called tack welds. Okay. So tack welds are not really used as a structural, final structural purposes, but it is used to start the welding, okay, to hold the things in place. Now, getting into more details about groove welds. So groove welds are relatively structurally more reliable, more robust, but they are harder to make. Okay. Um, as you can imagine, let's say you have these two plates. You have these two plates. This is first plate, this is the other plate. They are meeting together at this location. So for a groove weld, what you need to do is you need to have a small groove in between. Now that groove can be of square shape, that is the plates in their original shape as it is, but then there are limitations to how thick the plate can be. So if the plate is thicker than a certain limit, then you may not be able to have a square groove. Then you have to create some kind of a bevel or some kind of a V or some shape. So in this particular example, a V has been created, a V-shaped groove has been created. Okay, and you create this kind of a V-shaped groove, and then you deposit your this welding filler material into that groove. Okay, which will fuse with the base metal um, properly, and then uh, basically it is supposed to act as if the plate is homogeneous or monolithic. Okay, that is the purpose. So there is not much stress variation across the groove weld. That is the purpose of a groove weld. Okay, so generally the groove welds are of the type which is known as full penetration groove weld. So what does a full penetration groove weld mean? A full penetration groove weld means that you weld from this side and achieve the full penetration, or otherwise you weld from this side and also you weld from this side, so that the entire thickness of the plate is welded. Okay, and there you may also have partial penetration groove welds, but they are not usually very highly recommended. They may lead to a lot of other defects. So the full penetration groove welds are usually recommended for high quality structural applications. So that is known as full penetration weld when the weld extends completely through the plate thickness. Okay, so but it can be achieved from one side or it can be achieved from both sides, half from this side, half from this side. Okay, there are some benefits of this one, but there are some challenges with this one. The challenge is, I'll first talk about the benefits. The benefit is, first of all, if you are just having two plates coming together, okay, so then the plates may be just facing each other. They don't have to overlap. They can just be facing each other and they can be welded together. As long as you are able to maintain the perfect amount of gap that is required to provide the entire weld. If the gap is too much or if the gap is too little, your weld will not be proper. Okay, So that perfect amount of gap has to be made sure. As long as you are able to ensure that perfect amount of gap, exact amount of gap that is required, you can do a very good quality groove weld. And another advantage is that the stresses are quite straightforward, right? So let's say these two plates are supposed to be in tension eventually, and you provide a groove weld in between. Then the groove weld behaves just like the base metal. It becomes a part of the base metal structure. There is no geometrical complication because of the groove weld, and that's a good thing. Okay, so the stress flow is like before. Okay. So typically these kind of joints are known as butt joints. We'll talk about them maybe later. And this kind of a weld can be very easily be provided at corner joints. What do I mean by corner joint? So one example is this one. This is a groove weld. This was a fillet weld. I was saying that both these examples are more like textbook examples, but they are not as common in the field. In the field, let's say I want to make a box girder. Okay, so what's a box girder? It's a girder made of 4 plates. Okay, so let's say I have a plate here, and then I have a plate here. Let's say these 4 plates I'm putting together to make a box girder. Now, in this kind of a system, I want to do welding, right? So since these are, let's say, I'm going from this one first. So let's say this plate does not exist yet. I have not brought in this plate yet. I have these 3 plates, and I want to weld these 3 plates together, because I have to go step by step. So let's say I want to weld these 3 plates together, and I did all the tack welds and whatever is required in the beginning. Now I have an option to go with a fillet weld here very easily, right? So I've got a nice rectangular surface, and I will go for a fillet weld here, and I will go for a nice fillet weld here, which will, after it fuses, after the fillet weld, it will fuse these 2 base metals together, okay, and form a very nice fillet weld. And maybe I have calculated that it has sufficient strength to serve my purpose. That part is okay. Now I bring in the 4th plate, and now the situation is a bit more difficult. Now the 4th plate, I want the 4th plate to be flush with this edge. So this edge and this edge, I want them to be aligned perfectly. Right? So if that is the case, I cannot do a fillet weld, because for the fillet weld, I need 2 perpendicular surfaces. One option could be to extend the top flange and if I'm calling it web, let's say for the sake of this discussion, I'm calling it a web. So I can push this web back a little bit and extend the flange slightly outside, and then do a fillet weld here. Okay, fillet welds are easier welds to do. They don't require much preparation. But then what I'll have is not a flush surface here. This surface is projecting outside. The flanges are projecting outside. But if I don't want that, then I don't have any option other than going for a groove weld. So in these kind of situations, groove welds are the only alternatives. Okay. Similarly, there may be other situation. I want to make an I girder, I-shaped parallel flange girder. Or a T girder or whatever. So I want to make this kind of a girder. So I have got these plates of appropriate sizes brought in, and I want to weld them together. If I want to do a fillet weld, I'm usually required by the codes to do a fillet weld from this side, and then do a fillet weld from this side. The codes don't like if I do a weld only from one side. Okay. Experimentally, there is like research is not very clear about whether you can have a fillet weld only from one side, whether that is sufficient or not. But usually codes don't like it. So if you do a welding from only one side, that is very harshly penalized in the code. Penalty means you have to provide a very thick web or something like that to compensate for it. So you have to do two welds if you want to do this kind of a fillet welding. Alternate approach could be to go for a full penetration groove weld. Full penetration groove weld can be achieved only from one side as long as your web is thin enough. So if the web is not very thick, you can do a full penetration groove weld. Of course, it requires higher level of skill in order to achieve a full penetration. But if you are using one of these mechanized methods, it is not that difficult either. So that can be done, and that is definitely if you are able to achieve a complete penetration with complete fusion between the metals, base metals, that is anytime a better option than the fillet weld option. Okay, so groove welds have this advantage, but then the disadvantages are, as I mentioned, they are harder to make, harder to do. Why? Because let's say I have two plates and they have, I don't do any surface preparation. They have perfectly square edges. First of all, the edges have to be perfectly square. They cannot be uneven. If they are uneven, these edges, then the groove weld will be of very poor quality. So you have to make sure when you cut the surfaces, they have to be machined surfaces. They have to be ground surfaces. So after machining or after cutting with the gas cutter or something, again you have to grind them. You have to do some kind of a work so that you get flat, perfectly straight surfaces. If let's say you have uneven surfaces, then somewhere the gap will be more, somewhere the gap will be less, which is a very bad thing for a very good for a good if you want to achieve a good quality groove weld. Fine. So machining is required. So first of all, machining is required even to get this square surface. But further, what happens is that this square surface will be okay for a certain thickness of the plate. If the plate becomes thicker than a certain amount, then this square surface will be troublesome. Why? Because you have to put your electrode all the way through the bottom so that you are able to weld throughout the thickness. Even if you are able to approach it from two sides, still there is another limit. There is a limit to the thickness. So let's say the thickness becomes, let's say the plate is something like 16 mm or 20 mm thick. The electrode should be able to go all the way to the at least the half point or a little bit past the half point so that you can weld that portion. Okay, and then the gap becomes very large. If you want the electrode to go past, then the gap becomes very large. Then the material that you want to deposit there will not stay. That will keep falling off. It will keep flowing away from the gap. Okay, so therefore square kind of groove is not preferred that often, or it has limitations in terms of thickness of the plate. Then you can go for various kind of shapes. So you can cut the different shapes, grooves. So you can cut a V-shaped groove, you can cut a double V-shaped groove, that is, you want to do weld half of the weld from this side, half of the weld from this side. So you may cut double V. You may cut a bevel, you may cut a double bevel, you may cut a single U, you may cut a double U. So there are various types of grooves in which you can cut the plates. Okay, so most of these V and bevel are done through machining. Okay, this U and J mostly are done by plasma torch. So plasma torch automatically gives you a more curved surface. Okay, so you want to look for how a plasma torch works, you can just search on the internet, how does a plasma torch work. So it is basically just like a regular gas torch, but gas torch has a gas flame which is not a very nicely streamlined, so it has more unevenness, non-homogeneous kind of a damage to the plate. But plasma torch has works with plasma torch can be used with a higher level of precision. So if you want to cut a groove of a particular width, you can control the amount of energy that you are passing, or current that is passing through the torch, plasma torch, and then it will give out a kind of a flame which is basically plasma flame, that is much narrower and much more consistent in its size and length and so on, so that it can be used very effectively in getting a uniform geometry cut. So U and J kind of shapes. So in J shape you are cutting only one plate. In U shape you are cutting both plates. Okay, and then you may also require some kind of a backup plate often. What is the purpose of a backup plate? Anybody? What could be the, so backup plate is, for example, if you have this kind of a groove, you may put a backup plate here. You may tack weld a plate throughout the length of the weld. So this thing is, let's say, has a certain width in this direction. So you may weld a plate which is extending through the length of the weld right under the groove. What could be the purpose of the backup plate?
Balance,
Balancing of what?
like not to move, to be in same plane, to both the planes to be in same plane.
For that, you will have to do tack welding beforehand. Tack welding is almost a given all the time. So once you do the tack welding, you are holding the plates in place. The plates are not moving with each other.
So that the filler material doesn't fall out.
Yes, exactly. So backup plates basically prevent the filler material from flowing away. So otherwise, so let's say your gap is slightly more than what can be held in a that can hold the filler material in place. That may often be the case. So then you may have to put some kind of a backup plate. The backup plate is not welded throughout in the beginning. It is welded on tack welded only at a few locations, maybe 4 locations or 3 locations, so that it is held in place. It is holding the plates in place. And on top of that, but after you are done welding, then that backup plate will be at many places it will be fused together with the filler material. But it is very strongly recommended, especially for if you are requiring a ductile performance from the component or from the joint, that you remove the backup plate, which is a pain, which is a huge pain in the neck, cutting the backup plate off, because it gets fused at so many locations with the weld, and removing that backup plate off is a major headache. And because of all these complications, the groove welds are really not very liked in the industry. So as soon as you tell your fabricator that I want this weld to be groove weld, his cost requirements will increase by 4 times, something like that, for the same amount of welding. Yeah. So that is another challenge. And so basically groove welding has 3 challenges. One is achieving full penetration weld is relatively complex. You have to often approach the weld from 2 sides. So you want to weld these 2 plates, you have to weld half of it from this side, half of it from this side. That may not always be possible, correct? Because you may not have access from the other side. If you're making a box girder, you have access only from one side. You don't have access from the inside, right? So that may not always be feasible. So then achieving a full penetration weld from one side is even more difficult. Then you have to do the surface preparation, which is a V surface or U surface or bevel, whatever you want to make. That takes extra money, extra time, extra effort. Then the third thing is you may have to make special arrangements again to make sure that the material does not flow away. So if the gap between that root opening, that is marked as root opening here, if that is a little bit too large, and there is a fear that the filler material will flow away, then you have to provide some kind of a backup plate. And that backup plate, then you can leave it in place. Courts don't and force you to remove the backup plate, but leaving any such extra materials in place is bad for the health of the weld, because all such kind of plates lead to development of cracks in the future. So it is strongly recommended that you remove any such plate, backup plate and so on afterwards, which is again very expensive affair. It takes a lot of machining time and consumables and everything. Okay. If the 2 plates are not coming close together, let's say you are doing an assembly of a complicated assembly and not a single weld. So let's say I have 2 plates that I want to weld together. Groove weld may not sound too bad, because I can just bring the plates as close as I want and I can control that gap, because it's up to me. But let's say I'm making a big assembly and the plates are coming from 3-4 directions and all of them have to meet here and exactly fit. Now it's very difficult to get them to exact location, exact precise gap that I want. Some plates will be 1 millimeter away, some plates will be 1 millimeter too long, some will fit, some will not fit. And in that kind of a situation, getting the groove weld exactly perfectly fit is very difficult, and that leads to a lot of challenges. Okay. Between single V and double V, which one would you prefer? If you have an option to access the plate from the other side, which one would I prefer? Let's say I have 2 plates of I have the thickness of the plate does not change between the single V and double V. Of course, single V is more likely to be used when the plates are thinner. Double V is more likely to be used when the plates are thicker. But let's say I have same thickness plates. Then which one will be a better option?
Double V.
Sylvie.
Double V. Sorry?
Double
Somebody said
V.
double V. Yeah, and somebody else also answered it. No? Okay, why double V?
It is more symmetric and uniform.
Symmetric and uniform. Even single V, even though it may not look symmetric, if you see some videos and all, you will see that actually, since the material becomes, I mean, there is some kind of a over reinforcement or face reinforcement you have to do. Symmetry is not so much of a problem even for a single V. Plate behaves almost like a homogeneous material as long as you achieve full penetration. Anything else? Any other reason? If you see the amount of material that you have to remove and again fill. So first, in order to make that groove shape, right? So in a single V, let's say you want to maintain a certain amount of root opening. Okay, let's say you want to maintain 4 mm or 3 mm of root opening here, and then you want to maintain a certain angle because that is the angle required for you to be able to effectively reach the bottommost portion. So in order, let's say you maintain a 60-degree angle from here. This angle is 60 degrees, so this angle is also 60 degree. Total root opening, the total angle is 60 degree. So for 60 degree, the amount of the volume of this area or cross section area of this portion, that is the amount of material you had to remove and then again refill with the filler material of the welding. If you compare that with the volume or the area cross section area of this and this combined, which had to be removed and refilled, you will see that double V offers you a significant advantage. Okay, the challenge here is that you have to process the repeat the process twice. So you have to first machine one side of each plate, then machine the other side of the plate, then you have to weld from one side, then you have to turn the whole thing, weld from other side. So for thinner plates, it may not be huge advantages. So you may go for a single V, but if you go for a thicker plates, then double V is obviously more advantageous because the area that you have to remove or the volume of the material that you have to remove and you have to fill back is lower in case of a double V groove. Okay. Is that okay? Moving forward, fillet welds. So fillet welds are enormously much more popular than groove welds. And the obvious reason is that one, you don't have to do much surface preparation as long as surfaces are cleaned. You need to do some kind of a wire brush kind of a cleaning of the surface. You can grind them a little bit, but you don't have to take them to a machine shop and completely like flatten the surface. If some undulations are there, fillet welds can absorb them, accommodate them. Also, if there is not a perfect fit between the two plates, that is okay. So for example, in case of a groove weld, these two plates are being welded together, 1 and 2. And if the two plates are supposed to have a gap of 3 mm, you require a gap of 3 mm. You cannot say that, okay, let's have 5 mm some places and 8 mm some places. It will work for me. That doesn't work that way, right? The weld will not work. However, in case of a fillet weld, the plates were supposed to fit at this location, but even if there is a misfit, if 2-3 mm misfit, you can just clamp the two together and weld around it. As long as it does not have any other effect anywhere else, a little bit of misfit is okay because the plates can slide against each other, right? So instead of fitting the plates here, you will fit the plates here at a slight offset, but that's okay as long as it is not having any detrimental effect anywhere else. Yeah, so it gives you a lot of freedom to work with. Yeah, fillet welds. So they are especially used in lap joints. Wherever you have two perpendicular surfaces, they can be used. So in this particular case, you are using them. So you are using the face of one plate, face of this plate, and edge of this plate. So face of this plate and edge of this plate. These are the edges. So they can be. So you got two perpendicular surfaces. Out of the two surfaces, one is a face and the other one is an edge. Okay. Also, you can use it between two faces also, just like here. So just like in this example, this was also a face and this was also a face. So you were able to weld the two faces. Whereas in case of a groove weld, you are mostly required to weld between two edges. Sometimes you may have a face also. Like in this case, you have a face and an edge, but at least one of them will be an edge. Okay. So this is much more versatile type of a welding. No edge profession is required, less precision is okay, easy to fabricate, and as a result, almost 80% of the welds in structural engineering applications are fillet welds. Okay, so you can see the various types of various cases or various applications where you can provide it. So, for example, this in the first case, you have a gusset plate and you have an angle, and the angle has been welded to the gusset plate. Now, this surface you can see it is face versus face, two faces which are perpendicular to each other. One face is the face of the gusset plate, the other face is the leg of the angle, the leg that is projecting outside the screen, that leg, and the two surfaces are welded together using a fillet weld. And in this side, you are welding the edge of the angle with the gusset plate. Similarly, you can provide a gusset plate here, which is again a T joint and the column. You have a column base plate and a column, and around the column you can provide a fillet weld all around the column. Very common type of a joint. This is what the example I was giving about a box girder. So if you want to make a box girder, you have two flanges and two webs. Okay. So if you are willing to have a little bit of projection in flanges, which may often not be very liked by the architects or by the designers, but if they are willing to accept this kind of a projection, fillet welds offer the best and easiest solution. Okay. Built up sections, you can have an I section also. So all three of them are built up sections. If you have an I section, you are required to do the fillet welding on both sides. Generally, that is required. If you do fillet welding only on one side, it is considered as a bad kind of joint. But in the industry, I have seen all kinds of things being done, so I can't comment very much. This is also another type of a application for fillet weld, where it is very easy to do a fillet weld in comparison to a groove weld. Okay. Any questions about fillet welds or groove welds so far? Okay, so in the drawings, these welds are shown in various ways, because all the description of the welds, most of the description of these welds have to be provided in the drawing. Now, some of these drawings are at the fabricator level. So some of those are fabrication drawings, and they may not always be shown in all your structural drawings, but fabrication drawings have to have all those details so that the fabricator knows exactly how to go about. And there are manuals for welding, separate manuals for welding. Since that is beyond the scope of this course, I'm not going to go into too many details about how to decide when to back gauge, when to go for a V, when to go for a bevel, and when to go for a square, and so on. Those kind of things are more specialized. Only if you are going to specialize into welding joints, then you have to know all about all of them. Basically, what you should know is, if you see any of these symbols, you should know what kind of welding has been asked for and what would be the corresponding strength, because we are thinking from designer's point of view. We are not getting into too much into the fabricators domain. Okay, so a symbol like this, a triangle, okay, that is a fillet weld, which is different from a bevel groove weld. So the first symbol, that is fillet weld, that is here, and these are all different symbols for different shapes of grooves for the groove weld. Okay, so you may have a square, you may have a V, you may have a bevel, you may have a U, or you may have a J, and these are the symbols that are used. Okay, then if you have to do a backup plate, this symbol is used, a rectangle. A circle usually means that it's a weld all around, and a field weld, if you want to do a field weld, what is the difference between field weld and shop weld? Basically, often we are required to provide the details about the assembly process. So in the assembly process, some parts may be required to be fabricated in the shop. Then you take that sub assemblies, take them to site, put them together, and do a field weld. So field weld is at the site, and shop weld is the other one. So by default, everything is assumed to be shop welded, but if there is a weld that has to be done on the site, then it is marked as field weld. Okay, we'll see some examples of how to mark these symbols. Okay, so here what you can see is, this is one plate and this is another plate. Okay, so if I may draw these two plates in 3D. Okay, so that's how these two plates are. and the two plates are to be welded together using fillet weld. So this is how the fillet welds are supposed to be provided on the two surfaces, on the two edges. Okay, so since it's a back-to-back weld, right? So therefore, I have shown, it shows one rectangular. So rectangular triangle is the sign for fillet weld. So it has one rectangular triangle here and the other rectangular triangle right behind it, which means that it is the entire length is welded with rectangular with fillet welds on both sides. So this basically means welding on both sides. Okay, 5/16 indicates leg shown only on one weld. Okay, so 5/16 is the this picture I have taken from an American textbook. So therefore, these are inches. In India, you would write whatever number of millimeters you get out of it. Okay, so this size is 5/16 inches in this particular example. Okay, and why am I showing two triangles here? Because it is back-to-back weld throughout. Okay, this is another example. This one is another example wherein two fillet welds are provided between the two plates. Now there is some difference here. Here I have not marked the size of the weld. Okay, usually I should provide the size of the weld, but I'm not showing too many details here. Let's say the size of weld is mentioned before the weld. So size of the weld is mentioned before the weld. And when I say size, I mean this thing, this dimension. Yeah, that is the size. And then there is another dimension of this weld, that is the length of the weld. And sometimes we may have to specify the length of the weld also. In this, but in the first case, the length was not mentioned because it was throughout. If it is not mentioned, that means it is throughout the length of the or throughout the width. In this particular case, the length is mentioned, and what it says is that 2-inch long welds and intermittent and staggered on 4-inch center. So 2-4, it means that the weld is 2 inches long. Then there is a gap of 2 inches. So total distance becomes 4 inches. So the welds are 4 inches apart. So this is one end, this is the other end. So one weld is provided here. I'm not showing that much, that weld in much detail, but this one is provided here, fillet weld, and it is 2 inches long weld. Then it extends. Then there is a gap of 2 inches. Then another weld is provided. Okay, so this gap is also 2 inches and this weld is also 2 inches. So therefore the gap between center to center is 4 inches. The gap from center of this weld to the center of this weld is 4 inches. So 2-4 means this. And these two, unlike in this case, these two rectangles, not rectangles, these two triangles are staggered. What that means is that ideally I should not show the weld here. What it means is that there is a weld here, 2 inches long weld, and there is no weld here. So right opposite to this, on the other edge, there will be weld. Okay, so the welds on one edge are staggered against the weld on the other edge. Okay, so where there is a gap here on one edge, there are weld there on the other edge. So these two welds are not exactly at the same location, they are staggered, and that is emphasized by, or that is denoted by, this staggering of the welds. Okay, drawing a circle at this angle. So where this arrow changes its angle, that point, if you draw a circle around it, it usually means that weld all around. So in this particular case, you have a plate here and you don't have a plate here. This is a pipe. So you have a pipe. It's a pipe that is sitting on a plate. Okay. And what it is saying is that you provide a weld all around, and that is a fillet weld. This is a clear sign of a fillet weld, a rectangle triangle. Okay, so that is a fillet weld all around, and it means all around. For groove welds, you don't have those kind of rectangular triangles, right? You have groove shapes. So you may have a groove of rectangular size, rectangular shape. You may have a groove of V shape, sorry, bevel shape, you may have a groove of rectangular shape, you may have a groove of V shape. Fine. So there are 4 or 5 types of shapes I had talked about, right? For a groove, you may have rectangular, you may have bevel. Bevel is one surface is flat, the other surface is inclined, that is bevel. You may have a V where both surfaces are inclined. Then you may have J or U. So J or U also will be shown somewhat like this. You can find the symbols. So the symbols are shown here, right? So that's how. But what I'm showing you here are the rectangular, bevel, and V shapes. Okay. So in this particular case, you have rectangular on one side and bevel on the other side. The rectangular has a gap of 1/8 of an inch. So this is 1/8 of an inch gap. Single bevel, but with 1/8 of an inch root opening. So root opening is 1/8 of an inch. 45-degree bevel on upper piece. So one piece is, so this is the upper piece, this is the lower piece. So the upper piece is beveled at 45-degree angle and backing weld used. So backing weld is basically, because 1/8 is mentioned here, that means there is a welding to be done on this side as well. That is backing weld. In addition to that, another sentence, another phrase is written, which is saying back gouge. The back gouge basically means is, listen to me carefully. Basically, what you will do is, first you will machine the two plates in this particular shape. So this plate will have a rectangular edge here. This plate will have a rectangular followed by a bevel shape here. You will tack weld the two plates together with some gap maintained in between. Okay. Then what you will do is, you will, and that gap need not exactly be 1/8 of an inch. That's okay, but you will try to be as close to 1/8 of an inch, but it will not be exactly 1/8 of an inch. When you do the tack welding, it will get disturbed. So you maintain whatever gap as close to this gap as you can. Then you go about doing the first weld from this side. Okay, from this side. So this bevel edge. So you do the welding from this side. You start from the root and you fill that entire area. And you may not be, sometimes not be able to do the whole thing in a single pass. So you may have to do 2 or 3 passes. Okay, if this area volume becomes too large, then a single pass will not be able to fill that gap. So slowly, one after another, you have to go. And maybe 3 passes it may take, or 2 passes it may take to fill the gap. Once you are done filling with this gap, what will happen is that it will fill this gap, but this area will not be completely fused with the two plates. So then what you are required to do is, you are required to take a torch, a plasma torch or something like that, or just some kind of a grinder, whatever you can control properly, and cut some portion out from here and machine it and clean it. And that, at that time, you have to make sure that you clear at least 1/8 of an inch thickness gap on the back side. So 1/8 of an inch is about 4 millimeters. So you cut a groove of 4 millimeter. It would be partially fused already on this side by the time you finish this weld. So it is already fused partially, but it's not a very good quality. You will not achieve very good quality from one side. So then you need to create a groove. After doing half of the weld, you need to create a groove of the size mentioned here on the back side. That is called back gouging, which is basically removing the back side of the weld, gouging the back side of the weld. That is scratching it off, pulling it off. Okay, so you do that back gouging, then you do another weld from the back side, which fuses the three things together: the old weld, the two plates together, along with some new filler materials. That's why this shape clearly shows that you have to do another weld from this side. Okay. If it is a square groove, you just need to mark square. So if it is square groove only from one side, square groove and welding only from one side, you just mark it on one side. If it is to be welded on both sides, then you mark the square on both sides. Similarly, if it is a V to be welded only from one side, so you can see that V is cut and it is welded only from the top. So you draw a V shape like this. 3/8 corresponds to the root opening. Okay, so this is the root opening, 3/8, and then angle is 30 degrees. So total angle is 30 degree. This total angle is 30 degree. And then this rectangular here represents the backup plate. So that means you have to provide a backup plate, because there is a risk that this 3/8 inch opening will lead to flowing away of the filler material. So you need to provide the backup plate. Okay. Any questions now? Okay. So in comparison to bolting or riveting, welds have several advantages, and that's why welds are becoming more and more popular, especially in countries like India, where we don't work with very high level of precision, or our construction management is relatively poor. Uh, the communications challenges are there, so, and various teams work, and this thing has become more internationalized. Now, the expectation was that with the invent of all these software tools wherein all the details can be fed into a database from the very early, and expectation was that the level of precision in construction should improve. But actually in countries like India or in other developing countries, the bolting becomes a huge hassle, because the fit and all those issues are always nagging. So welding is a very attractive alternative. The advantage of welding, the structural side, the advantage is that for bolting you have to provide holes. When you do the holes in a plate, you reduce the effective cross section, so basically you reduce the effective strength of the members. In welding, you don't have to cut any holes, you don't have to reduce the cross section. So welding is does not really you don't compromise on the strength of the structural components. Okay, so that's a major advantage. If you have to sorry, if you have to provide airtight connections, then welding is the way to go, because bolting will always leave some gap in between. Even though you are doing friction grip bolts and all that, bolting may leave some kind of a gap, and then you have to provide some kind of a sealing material, right? So for example, if you want to, you have you noticed how the gas cylinders are made? The gas cylinders, the LPG cylinders that we use in our homes, how are they made? How do they make uh, this kind of a tubular body which is completely sealed from all sides? Are there any bolts in that cylinder anywhere? Yes or no? No, right? There are no bolts. Is there any weld?
Yes.
Yeah. Where is it? Where have you noticed the weld?
At the where the curvature comes,
Where the curvature comes.
at the top.
I'm talking about, see, basically how the cylinder is made. Cylinder is basically made of two cups. Okay. So you basically what they do is they take a plate and they put it into a die, and they hammer it several times until it takes the shape of a cup. So a hemispherical cup sort of a thing with some extended part. So that is one bowl. Similarly, they have another bowl, and the two bowls are brought together and welded together right in the middle. So if you have a LPG gas cylinder, go and check after this class. At the mid height, so you have the total height of the cylinder. At the mid height, there is a seam which is welded all the way around. That is basically two cups were brought together and welded using a groove weld. Okay. So, and you can use welding for providing this kind of airtight joints wherein the metal completely fuses together. And then there may be some welds which are used for holding other things, or connecting other components. So you may require welds to connect with that ring sort of a thing that is on the top. Also, there is a ring at the bottom. So those rings have to be welded to the plates, but that's a different, those are not really making sure of that there is no leakage in the in the cylinder. Okay. The leakage is prevented by the weld in the middle. Okay. So such kind of applications you can use it. So all these big containers that are used for LPG, CNG, whatever, they all have to be welded. Okay. It can be used in versatile geometries. That is very big advantage of welded connections. Let's say I want to weld two tubes together. Okay. So if I have one tube going in, circular tube going in this direction, uh, and then I may have another circular tube coming and meeting this tube in this particular location, and I want to provide a joint here. So this kind of a joint will be very complex if I were to go for a um, bolted kind of a joint. Okay. So, but with welding it is very easy. You just need to do a fillet weld all around this place, and there are manuals on how to do welding on tubular structures. Okay. So this becomes an obvious choice between complex geometries. Okay. They are more rigid than bolted connections because, as you may remember, bolts are usually more flexible than the structural components, right? So bolted connections are, first of all, there is a possibility of slip. Even if you resist the possibility of the slip, still bolts themselves are relatively more flexible in longitudinal direction, in shear direction, because you are not tying the entire surface. You are designing only for the required strength. In case of a welded connections, you have very small size weld, and that provides the entire strength. So they are much more stiff and rigid in comparison to bolted connections. And if you are going for a fillet weld, then you can manage with less level of precision, which is not possible in bolted connections. Whether you are going for a lap joint in a bolted connection, or whether a lap joint or a butt joint, precision is still required. Very high level of precision is still required because you have only so much tolerance. Otherwise, the bolt will not fit in the bolt hole. In case of welded connections, unless you are going for a groove weld, fillet welds, you can manage with a little bit of unfit. You can compensate for it. All right, so I think I should stop here today. If you have any questions, you can ask me now. No? All right, fine. So we will continue in the next class. Thank you.